So now that we've talked about the theory behind apparent weight versus true weight, let's look at it in the context of an example. Hopefully this will make it clear. The big thing with these questions is draw your free body diagram and have a lot of confidence in that free body diagram. So we have an 80 kilogram man. He is standing on a scale calibrated in newtons inside an elevator. We won't ask why he's doing that. We'll just go with it. So we want to determine the apparent weight of this man by the scale as the elevator is stationary, accelerating downwards at 1.10 meters per second squared, accelerating upwards at 1.10 meters per second squared, and moving upwards at constant velocity. So the trick with these questions, trust in your free body diagram. So part A, this person is stationary. So when we see that word stationary, we want to think net force is 0. That's really important. So if we draw the free body diagram for this person, well, there's a normal force acting up, and we also have a force of gravity going down. Now these two forces, they are going to be equal because this person is not experiencing a net force. So I can call up positive. It doesn't actually matter in this context. So I could just say that the net force acting on this gentleman, it's the normal force plus the force due to gravity. Again, net force is going to take a hike, so we don't need that. So we're going to get that the normal force plus Fg is equal to 0, or Fn is just going to be the negative of Fg. So to calculate this, Fn, it's going to be this person's mass. We have it as 80 kilos. And then G going down against my positive convention, I got to put that in as negative 9.81 meters per second squared. Oh, I better get my negative out front there. So I got negative 80 times 9.81. So this is going to give me about 784.8 newtons, or for sig dig purposes, about 785 newtons. Now that's the normal force. The normal force in our case is directed upwards. Remember, the key thing is we're looking for apparent weight though. So the apparent weight on an object is just going to be the negative of the normal force. All this means is they're changing the direction. That's it. So if Fn was going up, the apparent weight is just going to go down. So the apparent weight of this object is 785 newtons down. And that's it. That's all we're doing for that one. So in this case, because the object's stationary or the person's stationary, their apparent weight is of 785 newtons is going to equal their true weight, which is also 785 newtons. Now that's the easy case. Let's look at something a little bit more challenging this time. So this time the person, they're accelerating downwards at 1.10 meters per second squared. So this time the net force is not going to be 0. We're going to have an acceleration downwards. So we need a force of gravity going down, and we're also going to need a normal force going up. Now again, because we're accelerating downwards, we need Fg's magnitude to be greater than Fn because we need the net force down. Because the net force is down, I'm going to call down positive just to help me out. So this case here, we're going to write our net force statement. It's going to be Fn plus, or Fg plus Fn. Order actually doesn't matter, so I don't know why I'm fixing that. So again, we want Fn, so Fn is going to be this net force minus Fg. Or Fn is going to be Ma minus mg. Now we can see from our diagram, we can see that Fn is smaller than Fg, so we expect our apparent weight to be smaller than our true weight. We should expect the answer to be less than 785 newtons, just because that is our true weight. If we get something smaller than that, we can be pretty confident. If we get something larger than that, we got to go back and fix it. So Fn, all we have to be mindful of here is the signs. If you get the signs right, you'll be good. So we still have that mass of 80 kilos. The net force is going down, and I've called down positive, so we're going to enter the acceleration in as positive 1.10, and then we're going to subtract off the 80 kilos multiplied by the acceleration due to gravity. It is also down. We know that down is positive. So we're going to call this 9.81 meters per second squared, positive. Now, when we do this in the calculator, we're going to get a negative number, so we might not like that too much, but it's okay. So we're going to get about negative 696.8 newtons. The negative is here to tell us the direction. We've called down positive. The negative tells us we're going up. So that's good. We get that. And that's consistent with our free body diagram. Fn is directed up. The sign has told us it's going up. That's good. All we have to do for the apparent weight, well, the apparent weight is just directed in the opposite direction of the normal force. So if Fn's going up, apparent weight's going down. So the apparent weight for this object here is going to be about 697 newtons down. It's less than our true weight. We can be pretty confident with that. Part C. Only difference, this time we're accelerating upwards, so we want that normal force to be greater than the force of gravity. What that's going to tell us in this case is our apparent weight is going to be greater than our true weight. We can see that in the free body diagram. That should be reflected in our calculations. So for this, I'm going to call up positive since that's the direction of my normal force. Again, once we get our free body diagram, we always want to write that net force statement. So my net force acting on this object is Fn plus Fg. Again, apparent weight questions, we're always solving for Fn. So we got Fn equals this net force minus Fg, or Fn is equal to ma minus mg. So this question here, it's a bit deceptive. We get the same equation as the last time, but we have a different outcome. The only thing you got to be really careful with here, you have to be careful with the signs of A and G. This is where your free body diagram comes in. This is where your sign convention comes in. So we're going to be really careful with this one. So Fn, I still have my mass of 80. The acceleration's directed up, and we've called up positive. So we will put that in as 1.10 meters per second squared. And then we're going to subtract off this mass of 80 kilograms. This is where you have to be really, really careful though. G is going down, and we've called up positive. So we have to put G as negative 9.81 here. That's the difference. And that's the crucial thing we got to be mindful of here. So I'm even going to put an exclamation mark there. If you forget that negative, what's going to happen is you're going to get the same answers last time, and that's not really helpful to us. So this time we're actually adding these two parts together. So I'm going to get about 872.8 newtons, or for sig digs, we'll say about 873 newtons. Since this came out as a positive number, we're going to call that up. That's great that we get the normal forces up. Last thing, the apparent weight is the negative of the normal force, or the direction is just going to be down. So for this person accelerating upwards, they're having a slightly greater apparent weight, and that's to be expected. We expected that result. We confirmed that numerically. We're happy. And then the last one, D. Well, we're moving upward at constant velocity. Now, constant velocity implies net force is 0. Well, guess what? We've already done the situation where the net force is 0. We did that in part A where it's stationary. Do we need to do all the math again? Not a chance. We're just going to, if we know the net force is 0, we know the apparent weight is just going to be 785 newtons down. And this is the same as part A. If you're going to have the same work as a second time, don't bother repeating it. Just say, yeah, it's going to be the same as this case because Fnet equals 0. So hopefully by actually doing an example of this, this has cleared some stuff up.